going to look at Chapter 2 focus and Chapter 3 focus. They're the little sections at the end of the two chapters. The Chapter 2 focus has a variety of examples where we're asked to find models that can be constructed by using some geometric property of or algebraic property of the particular situation we're thinking about. So we're asked to find functions that model volume or area or surface area or distance. And here is a typical problem. So I'll do an example with you, and then I think I gave you like three, maybe four to do for homework. So we have 20 meters of fence to enclose a rectangular pen along an existing wall. So I'm just going to start by drawing a picture of what they're describing. So we have an existing wall. I'm drawing it in red because I'm imagining that it's brick. And then I'm going to build a fence along this thing. So one side of the pen that I'm building is going to be the wall. And I'm going to use fencing to build the other three sides. So it's like this. All right. So now I'll read sentence 2. Find a function that models the area of the pen. So I'm looking for area, right? Function for area. In terms of the length of the side opposite the existing wall. So that would be this side right here, right? The length of this side, which we'll call x. We don't know. So I want to find an area, a function for area, where x is the independent variable. Area as a function of x. All right, so if I have 20 meters of fencing and I've used x of it, how much do I have left? 20 minus x. And I have to build two sides of my pen using it, so I have to divide it in half. So I have 20 minus x over 2 as the length of each of these remaining two sides. Now, based on this picture, what is the area of this pen? X times 20 minus x over 2. Length times width. Now, if I were to simplify this expression I just came up with, this is like x over 1, right? And I'm going to distribute the x to both terms in the numerator. I'm going to divide the 2 into both terms, and I'm going to switch the order. So I'm doing a bunch of little algebraic manipulations in one step here. So, and you're going to come up with negative 1/2 x squared plus 10 x. Sorry, plus 10x. So if you don't see it, just do it all out on your own, okay, in the margin of your notebook. So I just did a little bit of simplification here. Now, what kind of function is this function a? You recognize it? Yeah, which is a quadratic, right? This is the general form of a quadratic. So the graph of a general form of a quadratic is always a parabola, right? Quadratics always are parabolas. Does this particular parabola open up or down? Yes, the vertex is on top, it goes down. How do you know that? The negative in front of the x squared. Perfect. So if I wanted to draw a picture or a graph, right? Here's x, here's area. Just graphing this, right? I know that it goes through the point 0, 0, because if I plug in 0 for x, I get 0 for y. So I know it goes through 0, 0. Which makes perfect sense, because if I were to try to build a pen that had one side of length 0, it would have no area, right? It wouldn't exist. So 0, 0 is on my graph. And then I know it's going to go something like this, because I know it's a parabola and I know it opens down. So what I'm interested in So I did the first part of the question. The first part of the question was to write the model, come up with a model of area as a function of x. Let's read the second part of the question. Find the dimensions of the pen that has maximum area. The dimensions of the pen. So they're asking me for this length and this length. Those are the dimensions of the pen. So what length should I build those so that the pen is the largest? So that there's the most area inside. Well, the largest area corresponds to this point right here, right? That's the highest area on the graph, highest value of A. How can I figure out the coordinates of this point here, this maximum of the function A? Sure. I could put it into standard form, find h and k. Okay, so h is always negative b over 2a. So that would be negative 10 over 2 times negative a half, which is 10. And then k we get by taking whatever you got for h and plugging it into the a function to get the y value. So this is a of 10. When I plug a 10 in here, 10 squared is 100, times negative a half is negative 50. So I have negative 50 plus 10 times 10. So I come out with positive 50. So this point is 10, 50. Another way you could have gotten that point is using your technology. So if I go to y equals, if there's anything in there, clear it. And I'm going to graph the function a. Negative 0.5x squared plus 10x. Window, well, x represents the length of fence across from the wall. And I only have 20 meters total, so 0 to 20, 20 would definitely be an upper bound, right? And then for y, for area, 0 would be the smallest area I could build. And then a large area with 20 meters of fencing. I don't know if I could do 20 by 20 would definitely be an upper bound because I don't have enough fencing for that. So let's say 400. And then I'll adjust as necessary. Okay, so I definitely need to adjust. My y value is too high, and my x value is not quite big enough to see the x-intercept. So let's go to the window, and let's maybe go to 100. And this maybe should go to like 25. Much better. So I want to find that maximum point. I want to find that high point. Use the command in the calculate menu, option 4, maximum. You give a left bound. And a right bound. And a guess. Oh, shoot. Ah, I screwed it up. There we go. Right, you just put the cursor somewhere between your left and right bound.
So how do you put that in standard form? Like you have the h and k, but
Yeah. Yep. A is negative 1/2. You have h and k. You have everything you need to make standard form if you want. So you see we get the same thing. We get 10, 50. And this is one of those cases where your calculator got really, really close and kind of like says, okay, I'm close enough. Where we know by doing the algebraic version, it is actually 10 by doing the negative b over 2a. Okay, so I'll come back to the standard form that you asked me about after we finish answering the question. So, what does this 10 represent? It's an x, yeah. An x in our problem was what? The length of the wall opposite, of the fence opposite the existing wall. Okay, so this is a length, right? That's one of the dimensions of my pen. What's the 50? Y value, and in this case, what are my Y values? Area. Yeah, this is an area. The question asked me to find the dimensions of the pen, right? The area is not one of the dimensions. They want me to find the length and the width. Area equals length times width. So if I have the length and I have the area, how do I get the width? Yeah. 50 divided by 10 says 5 would have to be my other dimension. So my answer to the question that they asked me is 5 meters by 10 meters. Are the dimensions I should use to build my pen. Yeah. But I think I know where you're going. And yes, we just need the x value because we know the width as a function of x, 20 minus x over 2. Right? So if I do 20 minus 10 over 2, you get 5. Right? So there's two ways we can get 5, either through the area or through the original diagram we drew. So we end up with an answer. You should build the pen 5 meters by 10 meters to get maximum area. And then that maximum area is 50 square meters, though they didn't ask us about that. All right, Audrey was asking, sort of as an aside, totally separate from what we were doing up here, what if I wanted to change this function into standard form? Negative 1/2 x squared plus 10x. Well, I already know h and k, right? Because standard form looks like this. A times x minus h squared plus k. And all I need to know in order to have the answer is what is a, what is h, and what is k. And then I just plop them into the equation. A is negative 1/2 because the a's in the two forms are the same. Ax squared plus bx plus c and a times x minus h squared plus k. They both have a in them because they're the same number. So I'm going to dump in a negative 1/2 here for my a. And then I have to replace h with something and replace the k with something. And I'm going to replace the h with a 10 and the k with a 50, because that's what I saw that I calculated them a little while ago. Minus 10 and 50. So you always subtract what h is. So the subtraction sign right here is part of the equation, not part of the value of h. So when I'm deciding what to put here, right, before I fill in the h and the k, I write x minus. And then I just write in whatever h is. If h is a 10, I put a 10 there. If h were negative 5, I'd put a negative 5 there. Right?
So you're not taking the sign into account in the
this form here? No. This 10 and this 10 are unrelated.
Oh, really?
Yes.
So how did you get
From h, negative b over 2a. I did negative 10 over 2 times negative 1/2, and it happened to come out to 10. It doesn't always come out to the same value. All right, so moving on to regression. So earlier this semester, we talked about how to enter data into your calculator and how to perform a linear regression. And now we're going to see what to do if that data is not very linear, if a line is not a good fit. The points are all really far away from it. So we'll go through an example together, and then I have several that I want you to try. Okay, so here's a table. It shows the number of women in the full-time civilian labor force in millions in some selected years. And I want to enter this data into my calculator and look at a scatter plot. So pull up the calculator. If you have a calculator, you should take it out and follow along. And if I go too fast through the steps of like what to type into your calculator, know that I included as the last page of your packet how to perform polynomial regression. So there's step by step what buttons to push on how to do this. Okay, so to enter data, I'm going to remind you how to do it. You press the Stat button and you choose option 1, which is Edit. If there's anything in there, you can clear it by highlighting the name of the list and pressing Clear. Okay. So then I'm going to enter the data, and I'm going to use 1900 as year 0. So this is going to be year 10 and year 30 and year 50. So 10, 30, 50, 70, 90, and 100.
So anytime that you have your aggregate last two digits?
No, not necessarily.
Well, okay, I didn't know if it could.
Yeah, you can measure time any way you want. You could say 1910 is year 0, and this would be 0. This would be 20 years after 1910. This would be 40. Does that make sense? So we can measure time. It's just all relative to where you start counting. Yeah. And using 1900 as 0 is just convenient. Yeah.
So that looks like, sorry, 1900 would be like x plus 10 plus 30. Right?
What is x? I don't know.
I don't know if you said that you started with 1900 or you started at 0.
Okay, so if I started at 0, the values I'd be plugging in here were 1910, 1930, 1950, which you can do. It's just I prefer to work with 10 as a nicer number than 1910. So I just set it up so that I can use nicer numbers. And there's no right or wrong way. You just have to decide which way you're doing and then stick with that throughout the whole problem. Correct, as long as it's not specified on the test. And in fact, I believe in your packet, it actually is telling you to let t be the number of years since 1900. So it told us to measure time this way. Okay, so then in list 2, we put the y data, the 7.4, the 10.8, 18.6, 31.5, 56.8, and 67.5. All right, so everybody have their data in? So to look at a scatter plot of the data, we should go to y equals. If there's anything in there right now, clear it, because we're not interested in that. That's from an old problem, right? And to be able to see data, you just have to put the cursor on plot 1 up here and press enter. And that turns the data plot on. So it'll plot your data. And then you just hit zoom 9, and that will pick a perfect window for data. Zoom 9, and we get our data points.
So this is like the line of best fit where you have to go in and a couple extra steps to get that line of best fit.
Yeah, we haven't done that yet. Yeah, we're just looking at the data. We're not trying to fit anything to it yet. Okay, so the next thing I want to do is I'm just going to do a regression line, the old thing that we already learned. Okay, I'm going to find the line of best fit, the equation for the line of best fit. So I'm going to quit out of the graph, go back to the home screen. And to get the regression line, you go to Stat, use the right arrow key to cursor over to the Calculate menu, and you choose option 4, linreg. And then you type list 1, comma, list 2, comma, y1, and you get y1 from the vars key. Right? Vars, yvars, function, y1. And you hit enter. All right, so I'm going to write down the equation here, and I get y equals 0.68x minus 7.8. And I'm going to use the r squared value instead of the r value. So this is a slight difference from what we learned before. We always looked at the r value. R squared and r are related in that r squared is what you get when you square r. So they're very closely related. The reason for using r instead of r squared is that r can be positive or negative, and it can tell you about the direction of the relationship. Is it a positive correlation or a negative correlation? When we're going to use a relationship other than a line, there's no such thing as positively or negatively correlated, so we use r squared. Use r squared instead. So we're going to use that from now on. R squared can only ever be positive, because when you square something negative, you get a positive. Square something positive, you get a positive. So the closer to 1, the better. Closer to 0, the worse it is. So my r squared value is about 0.915, which is pretty good. That's pretty close to 1. Uh-huh.
Does that have something to do with the distance from the
Yes, how far the points are from the line.
right?
Yes. It's exactly what they do. Yep. They take the sum of the squares. So let's just say I have 3 points, right? I'm going to find the line of best fit, like that. The way the calculator figures out the regression line is it takes the distances from every point to the line, takes each of these distances. So let's just call this one A, this one B, and this one C. Well, A is above the line and B is below the line. So one of those distances is going to be positive and one's going to be negative. So the way we take into account the fact that some are positive and some are negative, or we square them all. That way it makes them all positive. So a regression takes the sum of a squared plus b squared plus c squared, takes the sum, it adds up the square of all those distances and makes it small. As small as possible. No, it does the square. It does the square, yep. X values of what? This is a vertical distance, so the way you get it is by subtracting y values. Yeah. The distances? Residues. Yeah. Oh, is it residuals? Same thing, residuals, yeah. Okay. Residue, residuals, yeah. They're almost the same word. Yeah. Okay. Yeah. Yeah, if you're interested in this, you should take the stats class, this 114, Math 114. They go in, we don't do any of this in here. I only just showed it to you because somebody asked, right? But we just leave this all to our calculator. But if you're interested in it, you should take the statistics class. It's pretty cool. So yeah, that r squared value is a measure of how close it can get the line to all the points. Yeah, a, b, and c squared. Neither. That's just a sum. It's just a number. And then it makes that number as small as possible by putting the line in a certain place. Oops. Okay, so let's go back to the calculator. Okay, so if I did everything right here, when I go to y equals, the equation of the line should be in there. So I can just press graph and I can see how close the data points are to that line. It's not bad. It's not too bad of a fit. And 0.915 is not too bad of an R squared value. So this, we could be happy with this. We could say this is pretty decent. But let's just see what happens if we do a regression parabola instead of a line. I'm going to try to fit a quadratic to this set of data. So quit out of here, clear. And I'm going to do the same steps I do for linear regression. You go stat, calculate, but then instead of choosing option 4, linreg, choose option 5, quadrag. And then everything else is the same. You do list 1, comma, list 2. And then instead of using y1, I'm going to use y2 because I want to keep the line that I have in y1 there. So there's already something in y1, so I'm going to put the result of this guy into y2. So I'm going to do vars, yvars, function, y2. Hit enter, and it gives me the equation of a parabola. Ax squared plus bx plus c. So I get y equals 0.008 x squared minus 0.23x plus 9.4. And my R squared value is 0.997, which is much closer to 1 than 0.915 is. So it looks like, according to the R squared value, this is going to be a much better fit than the line is. So if I go to y equals, you can see now I have in y1 I have the line, and in y2 it's pasted the quadratic. So when I press graph, I can see the line, and that was a pretty decent fit, and then I see the parabola, and it's an almost perfect fit. So the quadratic is really a better model. Yep. Oh, okay. And it makes sense that a line would not be a good model for this particular data set because a line means constant, steady growth. But the number of women in the workforce is not increasing at a constant, steady rate. It's increasing faster and faster. The number of women enjoying the workforce is a bigger number every year than it was the previous year. So it makes sense that we should use a quadratic that goes up faster than a line does. There might be a correlation there. I don't know. All right, so now I want to use the parabola, the quadratic model, to predict the number of women who are working this year. So if I used 1900 as year 0, what's the year 2012? 112. So I'm just going to plug in x equals 112 into y2, because y2 is where I put the parabola, right? The line is in y1. So I'm just going to go to my table, and I can type 112 in for x, and it tells me what the line gives for y and what the parabola gives for y. And this particular question is asking me what the parabola gives. Table, second graph. So my answer would be 86.284 million. Which is significantly more than the line predicted. So having a good model is important, right? Even if the line was a pretty decent model, it's going to significantly underestimate the number of women in the workforce over time. So I'm going to show you another little nifty thing your calculator can do, which I did not show you when we did linear regression because you didn't know function notation yet, the f of x notation. Your calculator knows the f of x notation. So if you go to the home screen, I can tell it to evaluate y2 when x is 112 by calling up y2. So you hit vars, y-vars, function y2, and then put the x value in parentheses, just like you would for f of x. So this would be y2 at 112, and you get 86.28, the same thing the table gave you. So it's just a nifty little thing. You can use the table or this, you know, whatever you like.
So 68.799 is the last that we use for
Yeah, if we use the line to predict the number of women in the workforce in the year 2012, we would get 68.8 million. 18 million smaller than the parabola predicts. So how confident are we in this prediction? Explain what you mean by that.
Well, I mean, the way that the economy runs, yeah, ideally you get that people in there, but you get such fluctuations, and you get, what, 9 or 10% on it?
Right. Okay, this is
They
cool.
can get in the job market, but they'll be pink slipped in 6 months.
Right, right. So that's a really good thing to look at, is that even though we have a model that looks nearly perfect, we can't put all of our trust in it, right? Because there's yes, there are more variables than just time. Yeah, there are more things that affect the number of women in the workforce than just time. So this is a really important point, is that mathematical models are really, really powerful. They can help inform smart decision making, but they can't truly predict the future, right? They can make reasonable predictions, but they're not magic, right? It's math. So I can be reasonably confident because my data went up to the year 2000. 2012 isn't that far outside the data set. 12 years still, though, a lot of things can happen. And in fact, we did have a gigantic recession, right, between 2000 and 2012. So we can be reasonably confident. However, you know, it's not clairvoyant, right? We can't put all of our trust in a mathematical model.
I was going to say another strong variable would be if that's based on how many women occupy positions many. So that
True.
means, 10 million jobs
Might be like double job. Yeah, that's true. That's true. And in fact, I just mentioned this big recession we had. One of the huge reasons behind this recession is that people who were making decisions about how to invest a lot of money were doing these things called credit default swaps. And so basically, they put a lot of faith in mathematical models. They said, these things are amazing. We have a lot of data to support that we're going to make a ton of money. And they just weren't taking all the variables into account. They saw the equivalent of an R-squared value of 0.997 and said, this is a sure thing. And then it turned out not to be. Credit default swaps are kind of like, we don't need this, right? Okay, so we have a 4-step modeling process. One is to look at a scatter plot of the data. You just look at it, see what it looks like. And you say, should I use a line or is this data more curvy, right? If it's more curvy, you can use a quadratic or a cubic or a 4th degree polynomial, which we call a quartic. To decide which one you want to use, you look at the peaks and valleys. So last class, we said that a polynomial that has degree n has at most n-1 extrema, peaks and valleys. So if you have 3 peaks and valleys, you're going to need at least a 4th degree polynomial. Okay, so you're always going to count the peaks and valleys. You want to go one higher on the degree. Then let your calculator do all the work for step 2, right? Find an equation for the model. 3, verify that your equation is good. Look at it. See if the graph comes close to the data. Check the R-squared value. If it's not good, you want to go back and check, do I have a typo in my data? Or maybe you should just choose a different model. And then you can use the equation to draw conclusions, make estimates, and make predictions. All right, so I'm going to have you work on a few in your groups. And let me know if you have questions.